Hello everyone, this is the third video on electromagnetic theory. Here we are given two options of the relation between the electric field and electric potential. So which one is the correct option? Actually, the first one is the correct option. But why the negative sign? That is what we are going to discuss in this video. Before discussing about the relation between electric field and electric potential, first let us try to understand what are these quantities. Suppose you have a Wi-Fi router at your home and you are at a position P using your phone. For some reason, you want to change your location from point P to point A. Then when you change your position, two factors will come into play. One is the direction of your movement. Another one is the rate of change of signal with respect to the distance from the Wi-Fi router. Now, let us take another example. Suppose you have a charged particle Q and you have a reference point P and you want to change the reference point from P to point A. Now, if I take the analogy between these two examples, then the Wi-Fi router is equivalent to the charged particle and the strength on the signal, it is equivalent to electric potential, and the direction and the rate of change of signal strength is equivalent to the electric field. From the previous examples, now we can define electric potential and electric field. Electric potential is the strength of the influence of a charged particle at that point, whereas electric field, it is the rate of change of potential with respect to position. Additionally, electric field is assigned with a direction. Now, using this information, we can say that electric potential, it is a scalar quantity, and electric field, it is a vector quantity. Now, the next question is, how are both these quantities related? To understand this, let us discuss some basic concepts of calculus. Let us consider a function f which depends only on single variable. We can take the example f as a function of x is equal to sine of x. Now, if I try to plot the graph f as a function of x, then the graph will look like this. Now, if I try to take the derivative at each and every point, then it will look like a tangent at that point. Now, let us consider another case where the function depends on two variables, x and y. Now, if I try to plot f as a function of x and y, and then it will be a surface plot. Now, if I take y to be constant and take the derivative, then the tangent will look like this. Now, if I take x to be constant and take the derivative with respect to y, it will look like this. Now, if the function depends on a single variable, then it is the ordinary derivative. But if the function depends on more than one variable, then we have the partial derivative. If I have a function which depends on three variables, x, y, and z, then we can have the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Now, if I take all the three partial derivatives, and if I assign a direction, the partial derivative with respect to x is along the x direction, the second one is along the y direction, and the third one is along the z direction. Now, with this two information, I can form a vector. This vector is what we call as the gradient of f. Now, the gradient of f, this is a vector. But what is the direction of this vector? Now, if I want to calculate the change in f when we have an increment of dl vector, then the expression is given by this. This is a dot product between the gradient of f and the increment vector. Now, this dot product can be written as the product of the magnitudes and cos of the angle between the two vectors. Now, if I keep this increment vector magnitude to be constant, then df will be maximum when theta is equal to 0. But what is theta is equal to 0? It means the gradient of f is parallel to the increment vector. So using this logic, we can say that the gradient of f points in the direction of maximum increase in f. Now let us come back to electric potential. This is a scalar function. Now if I take the gradient of this scalar function, then it will give us a vector whose direction is along the maximum increase in the potential. Let us assume that this direction is from A to B. Then we can say that the potential at B is higher compared to the potential at A. This is what we have learned just now, that if the gradient of the electric potential is pointing from A to B, then B is at higher potential compared to A. Now let us take one more example. Let's say we have a minus Q charge and a plus Q charge. So the electric field lines will be originating from plus Q and it will terminate at minus Q. That is, electric field lines points from positive to negative. But the potential at plus Q is at higher potential compared to the potential at minus Q. You can use the formula 1 by 4 pi epsilon naught Q by R. That means I can say that electric field points from higher to lower potential. But in the beginning, we concluded that delta V points from lower to higher potential. Now, if you compare these two statements, they are opposite. So because of this, a minus sign has to come in the formula. Thank you for watching this video. If you want to see more such videos, then please subscribe. Thank you.